Hey everybody, in this next video lesson, we're going to talk about polarity of molecules. In a previous video lesson, we talked about the polarity of the bonds in a molecule, but today we're going to take a look at what happens when you combine all the polarity of the bonds into the molecule and looking at the polarity of the overall molecule. So I'm going to start you off with this question. Does the polarity of the individual bonds always create a molecule that's polar? Well, it might be possible, but what we really need to do is take into account the shape of the molecule. The shape of the molecule and the bonds together will result in the molecule being either polar or nonpolar. Now, what if the bonds were polar, but pulling in opposite directions? Does that have an effect on the polarity? Does the polarity of the bond pulling one way and the polarity of the bond pulling the other way have an effect on each other? How does symmetry play a role? Well, we're going to take a look at all of these here today. I'd like to draw your attention to this first molecule down here. This is the CO2 molecule, carbon dioxide. And as we know, if we calculate the polarity of the bond, this CO bond here on the right, carbon has an electronegativity of 2.55, and oxygen has an electronegativity of 3.44. And if we subtract those two, we get a difference in electronegativity of 0.89. Now that 0.89 is pulling to the right in this direction, but we also have the same bond pulling to the left. We can think of each one of these bond dipoles as a vector, and a vector has a length that is proportional to the size of its polarity and also a direction. So 0.89 represents a vector that is about the size of this arrow, and because it is pointing to the right, it's pointing towards a more electronegative element. But I have the same size vector because the polarity is equal to it, pointing in the opposite direction because the oxygen, once again on this bond dipole, is pointing to the left. Now if we factor in both bonds and the shape, because it's linear, these two bond dipoles cancel each other out. And what results is a nonpolar molecule, even though each of the bonds that make up the molecule are polar. Now let's shift our attention to this molecule here on the left. There are two different types of bonds in this molecule. We have the CO bond, which is the same as the CO bond over here. So we've got a polarity of 0.89 for the CO bond. And if I draw in the vector of the CO bond, it points towards the right with the same size as the vectors that we use for the carbon dioxide molecule. Now let's take a look at the polarity of the CH bond. Now H is 2.2 and C still remains 2.55. And so if I subtract those, you'll get a difference in electronegativity of 0.35. Now, if I were to draw a vector, because it's smaller than 0.89 that the vector is representing the CO, this would be a much smaller vector, almost half the size. And you'll see that they're pointing in towards the carbon now, rather than pointing out towards the hydrogen, because the carbon is more electronegative compared to the hydrogen. So I've got two vectors actually pointing in towards the carbon, and one large vector pointing out towards the oxygen. So if you kind of take the sum of each one of these vectors and add them together, what you see is that all of the electronegativity is kind of flowing in the right direction. And so this molecule doesn't cancel out all of the bond polarities. In fact, all the bond polarities are kind of adding to each other and showing an overall molecular polarity moving towards the right, towards the oxygen. And in this case, this is a polar molecule, and we represent a polar molecule not by a number like we do in bond polarity. Bond polarity is a quantitative value, meaning there's a number associated with it. We calculated the quantitative values of all these bond polarities. But a molecular polarity, it either is polar or it is not polar. It is qualitative. So let's tackle this last question. How does symmetry of the molecule play a role? Now, both of these molecules exhibit symmetry. This is a linear molecule, so it's symmetrical. If I draw a line down the middle, it's the same on both sides. And in this molecule, it's symmetrical as well, because if I draw a horizontal line, then and you fold it over, you'd get the same molecule on both sides. But even though they're symmetrical, symmetry doesn't automatically mean nonpolar. Symmetry on the right means nonpolar because the two bonds are equal, and so they're pulling equally, or sometimes you'll see the bond dipoles going in towards the center, so they're pushing equally. But if they're pulling or pushing equally in opposite directions, then they cancel each other out, resulting in a nonpolar molecule. But if the symmetrical molecule doesn't have the same bonds, the bonds are not all equivalent, then symmetry doesn't necessarily mean that it's a nonpolar molecule. In fact, in this case, we have a symmetrical molecule that has polarity because the bond dipoles don't cancel out. So in summary, the polarity of the molecule is dependent on the magnitude of the bond dipoles, but also the direction they're pulling or pushing and whether or not they'll cancel each other out. So symmetrical molecules don't always mean nonpolar. Now, we've had a linear and a trigonal planar molecule there, but let's talk about maybe a shape that has a pair of electrons on the central atom. Say, for example, NH3. NH3 in three-dimensional drawing looks like this. You've got a nitrogen in the middle, you've got a pair of electrons on top, you've got a hydrogen on the same plane, kind of going down and to the right, and then you have one hydrogen coming out at you and one hydrogen going behind you. Now, if you calculate the bond dipoles, because you have three identical NH bonds, nitrogen has an electronegativity of 3.04 and hydrogen has an electronegativity of 2.20. And if you subtract those two, you get a difference of 0.84. Now, if we draw a vector to represent that bond polarity, it would be pointing in towards the nitrogen, and it would have a length that is proportional to its size. So we've got a vector pointing in at 0.84 polarity, and that's going to be the equivalent size vector for all the other bonds. Now, if you look at the direction in which these are pointing, they're all pointing in, but also slightly up. So there's kind of an upward trajectory or upward motion in terms of where these vectors are pointing. All three of these are pointing in towards the nitrogen. Now, if I had a vector on the top that was pointing down that could cancel out these three vectors, then they would be canceled out and resulting in a nonpolar molecule. But because I don't have a vertical vector to cancel out the vertical components of these three that I know exist, then this molecule is polar. And this pair of electrons is the reason why. If I replace a pair of electrons, which doesn't represent a polar bond, it's just a pair of electrons, then it can't cancel out the direction or it can't cancel out the direction that the other three vectors are pushing. This is also true of other molecules with pairs of electrons on the central atom. Take water, for example. You've got H and O on both sides and two pairs of electrons on the oxygen. If you take a look at the difference in electronegativity of O minus H, what you get is 3.44 minus 2.20, or a difference of 1.24. Now, both of these are pointing up and to the middle, oxygen. But there is no vertical vector pointing down to cancel out the upwards vectors of the other two. And so because the pair of electrons are there, you get a polar molecule no matter what. So these last three bullet points are some helpful tips to help you identify the polarity of the molecules. The shape definitely plays a role. Any shape with a pair of electrons on the central element will always be polar. So that includes trigonal pyramidal and bent molecules because they can never have symmetry. Symmetry gives the opportunity for bond dipoles to cancel, although if the bonds are not equivalent, then they won't cancel. But symmetrical molecules have the opportunity to cancel, which is why they have a chance at being nonpolar. But trigonal pyramidal and bent will always be polar because they always have unshared pairs of electrons on the middle atom. Even if the molecule itself has nonpolar bonds that make it up, the bent and trigonal pyramidal nature of these molecules make them polar. A tetrahedral, trigonal planar, linear, trigonal bipyramidal, these molecules all are nonpolar, as long as all of the atoms on the exterior are identical. And if they're identical, then all the bond dipoles are identical, and they would all cancel each other out and result in a nonpolar molecule. Anything else, you would need to look at the polarity of the individual bonds to see if they are even and opposite. Well, that takes care of this video lesson. Thanks for watching.